Okay, the sound check, as usual, just in case. Yes, just 1 minute, and we'll start in a minute. I just need 1 minute to prepare for the seminar. I just want to open everything that I need. Okay, I believe we can start. Okay. Yeah, let's discuss everything that we have seen during the lecture. I just want to cover everything with examples. I want to compute everything that we met during the lecture. So let's start with a simple task. So let's take an integer from 1 to 10, and let's check for which n we have a field of n elements. So when there exists a field such that the amount of elements is n, let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How do you think? For which number do we have a field? For example, do we have a field with 1 element?
Yes.
Why?
No, I don't know.
Okay. Do we have a field with 1 element?
Why not?
Okay. In order to understand why not, we need to remember all the axioms, and there is one axiom saying that 1 is not equal to 0. So we have at least 2 elements in a field. So it's impossible to have a field with 1 element. Okay. Now, is it possible to have a field with 2 elements?
Yeah, 1 and 0.
Yep, Z2. The same thing happens with 3. Yep. Here we have Z3. Oh, here Z2. And here we have Z3. So let's skip 4 for a second. So by the same reason, 5 and 7, they will also give you a field as Z5 and Z7 because these numbers are prime. 2, 3, 5, 7 are prime numbers, and they give you a field just as this. What about 4? Do we have a field with 4 elements?
No.
Probably do you have any other option for the answer? Okay, so well, let me recall the result from the lecture. The result says that there exists a field. Well, okay, so if you have a finite field, field, then the amount of elements here is p to the n, where p is a prime number and coincides with the characteristic of F. So this automatically, well, that was the first part. And the second part was, if you take any prime number p and any n, then there exists a unique field F with p to the n elements. So if someone asks you, is it possible to find a field with 4 elements? What you should say, 4 is a power of 2, and 2 is a prime number. So there is a field which is called F4 with 4 elements, because 4 is a power of 2. By the same reason, there is a field with 8 elements, which is called F8, because 8 is a power of 2. And also there is a field with 9 elements, because 9 is a power of 3. But there is no field with 6 elements, because 6 is not a power of prime number, because 6 is a product of 2 and 3. It has 2 different prime numbers. And the same thing with 10. There is no field with 10 elements, because 10 is a product of 2 and 5. And this is not a power of a prime number. So this is not a power of a prime number. So this is a question which is easy to ask. So is there a field with this amount of elements? So you just check if this number is a power of prime element, and that's it. And don't forget that there is no field with 1 element, because in a field you need 1 to be different from 0. Just in case. Are there any questions regarding this problem?
No.
Okay, so I hope it's clear. But if you have any questions, just ask. Now, well, the interesting part is to produce such a field. Let's try to produce the field F4, okay? Explicitly. So let's produce a set and 2 operations on this set. So how to produce F4? Okay. So F4 is actually F2 to the 2. And let me recall the general procedure. The general procedure says, if you want to produce Fp to the n, you need to take the, well, first of all, you take a polynomial in Fp of x, where, let me recall that Fp is just the same thing as Zp, is just a different name. And the polynomial f must be irreducible, and the degree of polynomial f must be n. And then the required field will be this quotient. So as the set, it consists of the polynomials of degree strictly smaller than f. The addition is the usual addition, and multiplication is multiplication modular f. So you multiply 2 polynomials and then take a remainder modular f. So this is the structure of your field. So let's try to apply this procedure to produce F4 specifically. Okay, in order for this to work, we need to know what are the irreducible polynomials of over F2 of degree 2. And we have already calculated all the irreducible polynomials with coefficients in Z2. So, and we know there is only one irreducible polynomial of degree 2. X squared plus x plus 1 is the only irreducible in Z2 of x of degree 2. Because for the degree 2, being irreducible is the same thing as having no roots. Okay, so now the F4, by definition, is just z2 of x, quotient of x squared plus x plus 1. So it consists of the elements of the form a0 plus a1x, where a0 and a1 are from z2. And how do you multiply and add them? Well, the addition is the usual addition. And how do you multiply them? Well, if you want to multiply a0 plus a1x by b0 plus b1x, you do this. So you open the parenthesis and you write this a0 b0 plus a0 b1x plus b0 a1x plus a1 b1x squared. But there is no x squared here, so you need to take the remainder modular this polynomial. But this simply means that you need to, well, let me show you how you should think of this. In this ring, you think as if x squared plus x plus 1 is 0 in this ring. So if you move this to the right, well, you should write -1 minus x, but in Z2 there is no difference between -1 and +1. So you have x squared is actually 1 plus x. So now you just replace this thing by this thing, and this will be the result of the multiplication. So if you want to compute this, you will get a0b0 plus a1b1 plus here a0b1 plus a1b0 plus a1b1x. So this is the product of these two elements. So if you multiply this one by this one, this will be the result. This is how to compute in this field. And you may compute the result for each pair of elements using this rule. So this is how F4 looks like. So you can do whatever you want with this field.
I didn't really understand.
Okay, so should I repeat something, or you have some?
Yeah, can you like briefly go over the process, or maybe like give it an example?
Oh, okay. So first of all, I'm producing a field like this using this generic procedure. So if you want to produce a field like this, you just want to produce a ring like this where F is irreducible of degree n. Since I want to produce F4, and 4 is 2 to the power of 2, so P is 2 and n is also 2. So I consider Z2 of x and take a quotient by an irreducible polynomial of degree 2. So this was the first part.
So, oh, yeah. So I didn't understand why this equals, why that is of the form a0 plus a1x.
Oh, this part.
Yeah.
Oh, this is by definition. What is this ring by definition? It consists of all polynomials of degree strictly smaller than this one. That was the definition, how the set here looks like.
Okay.
So this is the definition. I mean, you consider all the polynomials of degree strictly smaller than f. So this is how this thing looks like as a set. So these are all elements here. But now you need to produce two operations, the addition and multiplication. And the addition is the usual addition, because you can, if you sum up these two polynomials of this form, you will get a polynomial of this form. Sum of two linear polynomials is a linear polynomial. But multiplication is trickier. And here is the way how to define multiplication. You multiply these polynomials as the usual ones. You will get a polynomial which need not be inside this set. You see, this is a quadratic polynomial, it's not linear. And now you just take the remainder modular this polynomial here. So you may compute the remainder by the usual algorithm, but here my goal, my point was that you may think of taking remainder in the following manner. You should think of this as something being 0 in this ring. So this expression is just 0 inside this ring. And since it's 0, it means that this thing is equal to this thing in this ring.
Yeah, I didn't understand. Like at one point you said that doesn't matter minus or plus.
Oh, because in Z2 you have well, +1 and -1 are the same, because -1 is 1.
Oh,
Because
but so in general, if it was some other
yeah, in general, but here we compute in Z2. The coefficients here are in Z2.
Oh, okay. Yeah,
Because everything what's going on here is for this specific ring. And here you see Z2 is the set of our coefficients.
Okay, yeah, thank you. Yeah, now we get it.
So, and you can see we have 4 elements here, 0, 0, 0, 1, 1, 0, and 1, 1. So if we list all the elements here explicitly, we will see 0, 1, x, and 1 plus x. This is the list of all the elements here. Okay, so now let's try. Okay.
May I ask you a question?
Yeah.
A small question. Why we can just sorry, why can't we say that Z4 is our field, for example?
Why Z4 is not a field?
Yeah.
Okay, let me show you why. Well,
I think it works for multiplication as well.
Z4 is not a field. Because in Z4, well, here I will use that 4 is the second power of 2. So let's take these two. So if you take element 2, it's a remainder here, which is a non-zero element, okay? But now if you multiply 2 by 2, you will get 0 in Z4. Each of these elements is not 0, but their product is 0. So you have 0 divisors. That's why Z4 is not a field.
But what's the problem with 0 divisors?
Okay, again, if it were a field, then each non-zero element must be invertible. So you can divide by a non-zero element because you multiply by the inverse element for a non-zero element.
And zero divisor can't be an invertible element.
Yeah, 0 divisor cannot be inverted.
Okay, thank you.
Yeah. And this, so this works for situation where this integer is not prime. So if it's a product of 2 numbers, then you can use the same argument. So that's why this guy is a field only when this number is prime. So let me clarify this. So Zn is a field if and only if n is prime. Yeah, it's very important. So you cannot produce such a field using just Zn or something like that with 4 elements. Okay. Are there any other questions?
Did you prove it on the lecture?
This one, yeah, it was several lectures ago.
Okay.
When we discussed rings. But I can tell you how to do this. Well, if n is not prime, it's exactly the way you prove this is exactly the same as we did it here for the ring of remainders. So if n is not prime, if you can decompose it like this, and these numbers are not 0 in Zn, but a and is equal, and you have 0 divisors. And if n is prime, and you take a from Zn, which is not 0, then a is strictly smaller than p, and it's not 0. So a and p are co-prime. So their GCD is 1. And now you can represent the GCD as the something like this. And then you take this expression modular p, and you get u times a equals 1 modular p, which means that u times a equals 1 in ZP. And u is the a inverse in ZP. So this is the reason why you need the extended Euclidean algorithm, because the extended Euclidean algorithm allows you to compute the inverse element in ZP. Okay.
Okay, thank you.
Okay.
Yeah, it's clear.
Yeah, but just in case, is it clear or not? Okay, now, so as you can see, F4 is this interesting thing. So yeah, and explicitly this thing consists of 0, 1, x, and 1 plus x. And we have these interesting rules. So how do you multiply these things? Well, you can write down the table for multiplication. Well, it's not interesting to multiply 0 by anything. You will get 0 everywhere. And it's not interesting to multiply 1 by anything, because you will get exactly the same element all the time. And so now it's interesting to multiply x by x. But when you multiply x by x, because we know that this one is equal to 0, then x times x is 1 plus x. So here you have 1 plus x. And how do you multiply x with 1 plus x? You will get x plus x squared. And x plus x squared is 1. Well, why? Because of this x plus x squared. If you move it to the right-hand side, you will get 1. And now the other thing you could do is to multiply 1 plus x with 1 plus x. Well, if you expand the expression, you will get 1 plus x plus x plus x squared. Well, x plus x is 0 because, well, 2 is equal to 0. So you will get 1 plus x squared. And 1 plus x squared is actually x. So this is the list of all possible products in your field. So this is the table for the multiplication. Are there any questions regarding this table? Just in case, who followed the way how I computed everything here? You can write plus in the chat as usual. Okay.
I have just one question. So
okay.
I guess I missed the part where you said, like, the notation, like what, like z2 of x kind of divided by x squared plus x plus.
How to pronounce this?
What is this notation? I kind of don't remember.
Okay, again, this notation. Okay, so, well, by definition, this thing is a set with two operations. So I need to so basically when I write this thing, I mean the set. So what is the set? The set is the set of all polynomials from here of degree strictly smaller than the degree of this polynomial. The degree of this is 2. So this thing consists of all polynomials of degree 1 or less. Here is the list.
If we just, like, instead of this polynomial, if we write x squared, then it would be the same, yeah?
Again?
So instead of x squared plus x plus 1, if we write x squared, it would be the same.
No, instead of, well, we should think of it as x squared plus x plus 1 is equal to 0. So this is how you should think of the properties of this ring. So x squared, so from this, it follows that x squared is equal to -1 minus x, but in Z2 -1 and minus x is the same as 1 and x respectively, so it's just 1 plus x. So this is the rule that you have to reduce the power, any quadratic power of your variable to a linear one, to a linear expression.
Wait, but again, where do we get it from? So we have
okay. Where did we get it from? Okay, so by definition, so I described you the set. Okay, now I need to specify multiplication and addition. The addition is usual, just the addition of polynomials. Okay, so yep. 1 plus x is just 1 plus x. 0 plus 1 plus x is 1 plus x. There is the addition is not interesting, just the usual addition of polynomials. But how do you define a multiplication? You define it like this.
Yeah, I see. Okay.
Yeah, you
so
you
by
take
that notation, you say which polynomial to use for multiplication. Yeah.
Yeah, this
Okay.
for this notation, yeah, I specify how the multiplication works.
Okay, thank you.
Okay, no problem. Are there any other questions? Okay, so now
I have a
if
question.
you, yep.
I did not understood how you calculated this.
Okay,
But
so
yeah.
first of all, is it clear how I computed the blue part?
Yeah.
Okay, now I want to compute the green part. So first of all, I want to compute x times x. So here should be x squared. But by definition, well, x squared is not here. So I should take the remainder modular x squared plus x plus 1. So I want to compute, I'm sorry, wrong color, x squared modular x squared plus x plus 1. And I'm saying that this is x plus 1.
Got it. Thank you.
So I apply this procedure for every part. So and how do I do this quickly? So I think of this expression. So x squared plus x plus 1 is equal to 0 in this ring. So if I want to compute x squared, then I can find it from these expressions. So x squared must be minus 1 minus x. So since minus 1 and minus x is the same as 1 and x in Z2, so so x squared is just this part. So if I compute something like x plus x squared, so x plus x squared, it's 1. If I find something like x squared plus 1, it's x. So this is the way how to compute it quickly.
Now it's clear. Thank you.
Okay. No problem.
Also, like, if instead of x squared plus x plus 1, we just had x squared, wouldn't it be kind of easier because we just remove
It would be
any...
easier, but it won't be a field.
Oh, okay.
Because x squared is not irreducible. You will have a nilpotent element. X will be a nilpotent because x is not 0 in such a ring, but x squared is 0.
Okay, yeah, makes
So
sense.
here, yeah. So yeah, you may use any polynomial, but the reason why we use this one, because it's irreducible. And this is the crucial part. Only for irreducible polynomials, you will get a field.
Okay.
Okay. Yeah, and here for Z2, there is only one irreducible polynomial of degree 2. So we have like the only one option. So there is no other way to produce such a field. Now, let's take all the non-zero elements here. F4 star. What is F4 star? Is the set of all non-zero elements. It's 1, x, and 1 plus x. From the lecture, we know that this group is cyclic. But, well, this group contains 3 elements. It's clear that this group is cyclic. So, well, by the Lagrange theorem, so let's say this is G. So G contains 3 elements, and this is a prime number. But the Lagrange theorem, we know that if you have a group with, well, and its order is prime, then every non-identity element is a generator. So these guys are actually generators of this group. So x squared is 1 plus x. For example, x squared is 1 plus x. And if you take 1 plus x squared, you will get x. So we have computed this in our table. You see, 1 plus x times 1 plus x is x, and x times x is 1 plus x. This is not a coincidence because, well, if you take a generator, its second power must be the other element, and the next power must be 1 because of the third power. And for this guy is the same. Its second power must be x, the other element, and its third power must be 1. So this is the structure of the multiplicative group of F4 star. This is how the multiplicative group looks like. Okay, so now I want to discuss some general things.
Wait,
Yep.
why is it a third power 1?
Why is what?
So we have, let's say, x, so x squared is 1 plus x.
Okay.
Then the next power we get x. But when do we get 1? I kind of don't.
Oh, no, it's not the next power. X squared is 1 plus x, and x cube, it's not written here, and x cube will be 1. It must be 1 because by the Lagrange theorem, because the order of the group is 3, so x cube must be 1. You need not to compute this.
But how do we compute it if we wanted to?
Okay, so how do we compute this? Well, you need to take the remainder modulo x squared plus x plus 1, and this will be the result. So how do you do this? Well, x cubed is x squared times x, and x squared is 1 plus x. Then you compute it like this, and now again, x squared is 1 plus x, so you write it x plus 1 plus x, and you cancel x, and the result is 1. So this is one way how you can do this.
Okay, I see.
Or you can use the division of polynomials. So how do you do this? X squared plus x plus 1. First of all, you multiply by x, and you will get x cubed plus x squared plus x. If you subtract, you will get x squared plus x, then plus 1. And if you you get x squared plus x plus 1. And if you subtract, you will get 1. And this is the remainder. As you can see, the result is exactly the same. But I prefer the first way of thinking, because you somehow just substitute one expression by another one, and you just simplify step by step the expression until you will get a linear expression. So you may use any approach. Okay, any other questions? Yeah, so this is an example of a F4. Let's discuss some general properties, and then I want to discuss F8. Okay, some general stuff. Well, I want to discuss a Frobenius automorphism. Well, strictly speaking, endomorphism. So what is this? Well, suppose F is a field, and the characteristic of F is P. Then we have a map phi, which takes x to the x to the power of p. Well, what I'm saying that this map is a homomorphism. Let's check that if we are given a field of prime characteristic P, then this map is a homomorphism. Well, what should we check? We should check three things. First of all, the identity must go to the identity. Then the product must go to a product. And the sum must go to a sum. Well, the first one is clear. Because 1, if you raise 1 to the power of p, you will get 1. So what about the second one? Well, it's also not very hard, because, what I wrote is absolutely nonsense. I'm sorry. I should write this. Yeah, I'm in a hurry. I don't know why. So I need to check this. Yeah, so my map preserves multiplication and addition. What about multiplication? It should be clear, because the left-hand side is AB to the P, and the right-hand side is A to the P, B to the P. And it's clear that this is true, because multiplication is commutative. You can rearrange the other factors, and this is true. So this is also okay. So this was okay. This one was okay. So now we want to check the rule for the addition. So let's check. What do we need to prove? The left-hand side is a plus b to the p. And what is the right-hand side? It's a to the p plus b to the p. So why is this true? How to check this? Well, in general, this is not true. But here we need to use the fact that F is a field of prime characteristic P. So, okay, so let's expand this expression. So what will we get? We will get a to the P plus CP1 a to the P minus 1b plus CP2 a to the P minus 2b squared plus etc. CP and P minus 1 AB to the P minus 1 plus B to the P. Just in case, there are two different notations for binomial coefficients. So either this one or this one. Well, I prefer this one because of the Russian schools. But if you're not familiar with this thing, so this is exactly this one. And how do you compute this? By definition, it's P factorial over K factorial P minus K factorial. So this is just the definition of this coefficient. So this is how to expand this expression. So as you can see, this thing is this one, this thing is this one, and we need to show that all of these summands are zero. In order to do that, let's prove that each coefficient here is divisible by P. So what we want to show that P divides this expression when K is like this. So if we can prove this, then you see each coefficient here is divisible by P. But if you have a field of characteristic P, then if you sum up several elements of P times, you will get zero. So let me show you. So if we have an element X from your field F, then X plus etc. plus X P times must be zero if the characteristic of F is P. So let me show you. So I just to be clear, I just want to stop here, and I want to prove some additional claim. So if you have a field of characteristic P, we know that 1 plus 1 plus 1 P times is zero. But actually, from this, it follows that X plus X is zero if you take P summands. So why? Well, because you can rearrange this sum as follows. You can rewrite this as 1 plus 1 plus 1 P times, P times X. Just by definition, if you expand this expression, you will get 1 times X plus 1 times X plus 1 times X, and 1 times X is equal to X. So this is exactly the same thing. By the definition of the characteristic, this expression is zero. So 0 times X is actually zero. So in a field of prime characteristic, if you consider X plus X P times, you will get zero. Roughly speaking, this means that if you consider P times X is zero in a field of prime characteristic P. So if we can show that this number is divisible by P, this expression is P times something in a field F. So it must be zero by this claim. So if this is divisible by P, then the whole expression is represented as P times something, and it's also zero by this claim. So the red part will be zero if we can prove this. So now, just in case, are there any questions at this for this part? Okay, so now how do we prove this? Just in case, who thinks that he knows how to prove this? Is there anyone who knows why this is true? Okay, let me show you. So just by definition, this expression is this p factorial over k factorial minus p minus k factorial. And we know that k is between 0 and p, and not equal to the 0 and p. So you see, what is the factorial? Is the product of all integer from 1 till the number p. And by the definition, 0 factorial is just 1. Okay, so as you can see, the numerator here contains p. So the numerator is divisible by p. But if you take a look at the denominator, then here you have 1 times 2 times, etc., times k, and k is strictly smaller than p. So here there is no p here, because here you have product of smaller numbers. Also, since k is strictly larger than 0, then p minus k is also less than p. And here you have product like 1 times 2 times, etc., times p minus k. And there is also no p here, because p is larger than any element here. So the numerator is divisible by p, but the denominator is not divisible by p. So when you compute the expression, and you know the result is integer, so the resulting integer number is divisible by p. So that's why p divides this expression, and that's why the claim holds. Just in case, let me recall. So we need to prove this equality. So we expand the left-hand side, we get this expression, and we want to prove that each summand here is 0. We prove that each coefficient here is divisible by p, and because the characteristic of the field is p, each summand here is 0. So that's how we get this equality. And this completes the proof that this map is a homomorphism. And this homomorphism is called the Frobenius endomorphism. Just in case, who thinks that he understood the whole proof of the fact that this is a homomorphism? Could you write plus in the chat? Or if you don't understand at least one detail, could you write minus or plus minus just for me? Okay, Kirill, do you have any questions?
Yeah, just keep it. I understood that p is a prime number. That's why p divides our k from p. Choose k from p, right?
Yeah.
But what next?
Oh, so the next, you see, then this expression, so let me say, okay, let me write it here. I said this orally, so it's, for example, when you have this, you can rewrite it like p times something.
Yeah, sure, I get it, yeah.
Okay. But
like we can divide it into 1 plus 1 plus 1 plus 1, and
yeah, and you take, and this is your x.
Okay.
Yeah. So this is 0.
Okay, thank you.
No problem. Okay, are there any other questions? Okay, so before of this property, let me show you how to simplify several computations that we did. For example, when we dealt with F4, we wanted to compute in this field the product x plus 1 times x plus 1. Well, how did I do that? I expanded the brackets. I expanded the expression, and I canceled x and x. But now we see that this is x plus 1 squared. But this is a field of characteristic 2. So if I raise this expression to the power of 2, this is exactly the same as raising to the power of 2 each summand, because raising to the power is a homomorphism. It preserves the sum. Yay! This is probably the best part of this. So now this is just x squared plus 1, and then we can reduce it by x squared plus x plus 1 and get x. So this is the place where you can raise an expression to a power very quickly. So when you know the characteristic of the field, it's really easy to raise to the power of the characteristic. So if your field is something like if your field has characteristic 3, it's really easy to raise to the power of 3, and so on and so on. So this is how it works. Okay. Well, now the next part. Well, what happens if what happens if we take a finite field? Well, suppose F is a finite field of characteristic P. Well, it must be a finite characteristic. Then what I'm saying, before doing that, I'm sorry. Before switching to the case of finite fields, I just want to make one additional remark. Well, so we have these map from F to F, which is raising to the power of P. So here the characteristic of F is P. So this is a homomorphism. But each homomorphism of a field is injective. Why? Well, because if you have a homomorphism, how to prove that it's injective? We need to show that the kernel is 0. But the kernel is an ideal inside the field. But each field has only 2 possible ideals. Well, there are 2 options. Either the ideal is 0 or the ideal coincides with the whole field. So in the second, the second option, just in case, I think I should explain this, but let's skip this for a second. I'll explain it in a minute if you don't understand why this is true. So what I'm saying that every field has only 2 possible ideals, the 0 ideal and the whole field itself. So there are no other options. And what does it mean that the ideal coincides with the whole field? It means that phi of x is equal to 0 for all elements from F. And this is not our case, because in our case, phi takes 1 to 1. So this is not our option, because in our case, phi of 1 equals 1. So this is not our case. So in our case, the ideal must be 0. And since the ideal is, since the kernel is 0, the map is injective. So what I'm saying here, that this homomorphism is injective. Well, actually, what we have proven here, that every homomorphism of fields must be injective. Well, it never has a kernel. So the only thing that I need to explain is why we have these 2 options, why there is no other ideals except 0 and the whole field. But is it clear what happens here modular this fact? Are there any questions regarding what happens here? Just in case, Kirill, are you okay with that?
More or less.
No?
Why do we have only 2 ideals?
Well, I mean, modular this fact. Is it clear what happens here modular this claim? I will explain it in a second, but if you use it as a black box, is it clear what happens here?
No.
No.
Could you just go through it again quickly? Very quickly.
So what I'm saying here, that this map is all, since this map is a homomorphism, it's and F is a field, then this map is automatically injective. So this is what I'm saying, that this map must be injective.
Okay.
And how do I prove this? Well, actually, the right claim is that every homomorphism of fields is injective. And this is how you prove it. In order to prove that your homomorphism is injective, you need to prove that its kernel is 0. Is it okay?
Yeah.
Now, what I'm claiming that in a field, every kernel is an ideal. And I'm claiming that an ideal in a field is either 0 or the whole field. So this is as a just use this as a black box.
This one, yeah, this
Yeah.
one's clear.
Yeah, and the second part is impossible here because one must go to one by the definition of a
Okay,
homomorphism.
but
So
why do we know that kernel is ideal?
why? But
Ой,
that
чё я говорю уже?
the kernel is always an ideal. That was one of the claims about the rings. If you have a homomorphism of rings, the kernel is an ideal. So the reason why we have ideals, because the ideals are the kernels of homomorphisms.
Okay.
Well, that was the general claim. So you may read the lecture notes and you'll see, but you can check it because it's closed under addition. And if you multiply something from the kernel by anything outside of the kernel, you will get, again, an element which goes to 0, which means that the product of something inside the kernel by something outside of the kernel is also inside the kernel.
Okay, good. Okay.
So now how to prove that we have these two options? You see, well, now I want to prove this. Why this happens? Well, if I is equal to 0, then we're done. Now we may suppose that I is not equal to 0. So there is at least one non-zero element in X. And we want to prove that I coincides with the whole F. But by the definition of the ideal, if we take element from the ideal and we take any, since we're in a field, there is X inverse in F, not necessarily inside the ideal, but in F, for every non-zero element, we have the inverse element. But then if you consider this product, then this one is from ideal and this one from F. So the result must be from the ideal by the definition of the ideal, because the product of something from an ideal with the something, with something from the ring must be inside the ideal again. So, but this product is 1. So first of all, we see that if we have a non-zero element inside the ideal, we have the element 1 inside the ideal. But now, if you take an arbitrary element from the field, you can represent this as the product of y and 1. And as we can see, 1 is in the ideal and y is in our field. So by the definition of the ideal, it must be inside the ideal. So this is how you prove that every element of F must be inside the ideal if the ideal contains at least one non-zero element. Kirill, is it clear now?
Yeah, it's clear.
Okay. So what I'm saying that this map, so it follows that the map of this form is injective if the characteristic of F is P. In particular, if you solve an equation like this, there is at most one solution. So it may happen that you cannot extract pth root from an element B, where B is an element of F. But if you can, there is only one possible solution. And if you have alpha from F such that alpha to the P is equal to B, then okay, so then you can do it like this. So X to the P minus B is equal X to the P minus alpha to the P, and this is equal X minus alpha to the P. For example, you can split these polynomials to linear factors like this. So raising to the pth power is injective, so it means that you can extract only one root of pth power if it exists. And now, if F is also finite, then this is an injective map between finite sets, and it must also be surjective. So if F is finite field, then the map phi from F to F by this formula is bijective. Well, because it's an injective map of the finite set to itself. But such a map must be surjective. There is no other options. So this is how it works. Are there any questions regarding taking these routes? Okay. Let me see what I want to do next. Okay, let's deal with the field f of 8. I want to discuss the other field f of 8, and I want to discuss I want to recall how to find a generator of the group it has. Okay, so now I want to compute f of 8. How do we do that? Well, 8 is 2 to the power of 3. So we need to take a polynomial in z2 of x of degree 3. And then f of 8, yeah, and this polynomial must be irreducible. Then, that was a mistake. Then f of 8 is what? It's z2 of x over f. It's just by definition. Well, that was the procedure we used. So we need to find an irreducible polynomial of degree 3. Well, it happens that there is a lot of them. There are several polynomials of irreducible polynomials of degree 3. We actually have computed all such polynomials the previous time. Give me a second. There was a list. Yeah, so there are two, as I can see, there are two polynomials. What are them? So we have x cubed plus x plus 1, or we have x cubed plus x squared plus 1. These are two irreducible polynomials of degree 3. So we just know the answer. So we can use either of them in order to compute. Well, let's use one of them. Which one do you prefer? Well, let's take this one. So f of 8 must be z2 over x modulo x cubed plus x plus 1. Well, this simply means that all the elements here are polynomials, are quadratic polynomials of this form, where a, b, and c are from z2. So we have 8 elements of this form. And when you multiply these elements, then x cubed, so how you should think of this, x cubed is equal to 1 plus x. This is how you think of it. Now, what is f8 star? So, and yeah, you can use this formula to deal with this polynomial, with this field explicitly. So you can compute any product of any elements. So it's enough to know this rule. Now, what is f8 star? Well, it must be a cyclic group, but how many elements does it have? F8, by definition, has 8 elements. F8 star contains all the elements of A star, but the 0 element. So it has 1 element less. So the amount of elements here is 7. It's also a prime number. So, well, actually, every non-zero element here, is a generator. Or no zero are every non-identity element. So you can take every element G from F8 star such that G is not 1, then G is a generator. But this is because the order of this group is prime. By the Lagrange theorem, this is one of the corollaries of the Lagrange theorem, then every non-identity element is a generator. Okay, but from the other hand, you may produce this ring using the other polynomial, well, I mean this field. So you may produce the field F8. Well, let me rewrite the previous definition. So you use this one, and in this ring, x cubed is equal to 1 plus x. From the other hand, you have a different polynomial. And for the other polynomial, you have the different way to produce this field. Let's say this will be like 1 and this 2. Well, it's not a good way of putting notation here, but I need some way to specify which construction I use. So this is the second irreducible polynomial of degree 3. And in this ring, we have a different rule for multiplication. X cubed is equal 1 plus x squared. So the general theorem from the lecture says that these two fields are isomorphic because there is only one field up to isomorphism of this order. So for each order, there is only one field, only one finite field up to isomorphism. So we have produced, well, it looks like we produce different fields with different operations, but we can find an isomorphism from one field to another one, which explains that this is actually exactly the same field. Now I want to discuss the way how to find an isomorphism between these two different implementations of your field. But before doing that, is it clear what's going on here? Should I explain anything or repeat or maybe clarify the details?
Well, I have only one question.
Yep.
What is F8 star?
Oh, F8 star is the set of all non-zero elements, the set of all invertible elements of your field.
Okay, thank you.
Yeah, you have like one element less. So, and now, well, just let me summarize what has happened here. We have a way to produce a field of 8 elements. And in order to produce such a field, we take a polynomial of the required degree, and this polynomial must be irreducible, and then this procedure gives you a field F8. But since we have two different polynomials, irreducible polynomials of degree 3, we have two different constructions for F8. And now I want to find an isomorphism between these two things. Okay, in order to do that, I want to discuss a different problem. Because what does it mean to find an isomorphism? We need to find, well, how to find an isomorphism? We need to find a homomorphism from one field to another. And then we want to prove that this homomorphism is an isomorphism. So first of all, the interesting question is how to find a homomorphism from a ring like that to a ring like that. And there is actually a general claim. Well, if we have a field K and a ring R containing this field K, and we have a polynomial f from K of x, and we have ring K of x quotient f, and we want to find a homomorphism phi from the left ring to the ring R with additional property that f of k is equal to k for all k small from k capital. So this is our context. So what are we given? We're given a field k, so this is a field, we're given a ring R, so this is a ring, and we're given an irreducible polynomial, which give, oh no, not irreducible, but any polynomial. This is just any polynomial. So kx, so in the general case, this one is just a ring. This is not a field, but this is a ring of remainders. And we want to describe all homomorphisms from this ring to any other ring containing the field K with additional condition. The condition is here. This homomorphism must take all coefficients to themselves. So it doesn't modify the coefficients. So how to describe all such homomorphism from here to here? And there is a way, yeah, this is the task number 5 from the previous seminar. So I didn't have enough time to discuss this task, but now this is the place where I want to discuss this task. So are there any questions regarding the task where I'm solving? Should I explain anything? Okay, so now let me tell you the answer. Well, what you should do is this. First of all, I want to denote the set S. What is S? Is the set of all elements of the ring R such that R is a root of F in this sense. So I just take this polynomial F and I substitute an element of R in this polynomial. This will be an expression in R. And I wanted the result to be 0. So I find all elements from R being roots of F. Then it turns out that all homomorphisms from here to here are in one-to-one correspondence with this set. And here is how these homomorphisms work. If I choose an element R from the set R, or S capital, then I define a homomorphism phi R, and this is how phi R acts. It takes a polynomial g of x from here, I'm sorry, and it takes this polynomial to g of R. So this is the rule for the homomorphism. And all the homomorphisms are of this form. So there is no other homomorphisms from this ring to this one. So you just find a root here of this polynomial f, and then you just substitute this root instead of x. And this is how your homomorphism works. Now, there are two things we need to do. First of all, we need to show that this rule is indeed a homomorphism. So we need to show that this is a homomorphism. And the second thing, we need to show that any other homomorphism is of this form. So there is no other homomorphisms. So let's check that this guy is a homomorphism. So how do we do that? Well, we need to show that phi R takes 1 to 1. Phi R takes sum of polynomials to the sum of results. I'm sorry. And we also need to check that phi R preserves the multiplication. So these are things that we need to show. But the property number 1 is clear, because if you take a polynomial, g of x being 1, if you substitute anything instead of x, you will get 1. So 1 goes to 1. Well, it's so this one is clear. Now, the same thing happens with addition, because how do you add polynomials in the ring of remainder? You just add them as usual polynomials, and then you substitute the result. So you just do something like this. First of all, you find the sum of polynomials, and then you substitute the element R. This is the left-hand side. And what is the right-hand side? You first substitute your element into each polynomial, and then you add the polynomials together. But okay, this is also clear just by the definition. the left-hand side is exactly the same as the right-hand side, because how do you compute the sum of polynomials? You just sum all the coefficients, and how do you compute the right-hand side? Again, you can sum the corresponding coefficients. You can add the corresponding coefficients together. So the only interesting question is what happens with multiplication. And as you can see here, we didn't use the fact that R is a root of the polynomial f. So now, how do we compute this part? First of all, we need to compute the product, but how do we compute product? We compute the product as usual polynomials, and then we consider the remainder modular f. So here, the degree of R is strictly smaller than the degree of f. So R is the result of this product in the ring of remainders. Oh, R is a bad notation here. Let me use a different name. Let me use H, because R is already taken for the element R from the ring. So yeah, so H is the remainder. And now we need to substitute the remainder, the root R inside of H. This is, by definition, the left-hand side. But how do we compute the right-hand side? In the right-hand side, we first substitute R into each polynomial, and then take a product inside R, the ring R. So we need to prove that these are the same where? In the ring R, because these expressions are written in the ring R. But now, we remember that we have this equality of polynomials. This is the equality of polynomials. So I can substitute into these polynomials R instead of X, and we will get G1 of R, G2 of R equals Q of R, F of R plus H of R in R, capital. So this equality follows from this one. When I substitute R instead of X, since the left-hand side and the right-hand side are exactly the same polynomials, if I substitute exactly the same element on the left and the right-hand side, I will get exactly the same result. And these are results I'm getting. And here, I use the fact that this one is 0 in R, because R small was the root of polynomial f. So we can cancel this summon, and what remains is exactly what we wanted to prove. So as we can see, that this rule defines a homomorphism. Okay, is there, just in case, who thinks that he can, who thinks that he or she can, she followed the whole proof?
I have a question.
Yep.
What is that?
What again?
Our function f, we have a set S and there is a function. What is f is just of a reminder.
Well, S is the set of roots here,
okay.
of the polynomial f. And for each root, we define a homomorphism phi r from here to here by this formula. And what was going on here, I have checked that this rule defines a homomorphism. So this is actually a homomorphism.
Okay, gotcha.
Okay, now the reason why every homomorphism is of this form, well, you should, well, if you take an arbitrary homomorphism, well, I'll tell you how to do this, but I just want to skip because it's very similar to the things that we did. So if you take an arbitrary homomorphism from here to here, then, well, you see f of x is equal to 0 in the left-hand side. So what is f? Well, f is something like this. And it's equal to 0 in the left-hand side. So if you apply phi, you I'm sorry. Let's do it in a different way. So let's take x. It must go to an element phi of x. Let's denote it by r. So the claim is that r is the root of f, and the second claim that phi coincides with phi of r. So let me clarify why this element is the root of f, and the reason why phi coincides with phi of r is just a routine. But so if you have f, an expression like this, so this is equal to 0 in the left-hand side. So when you apply phi to the left-hand side, you will get a0 plus a1 phi of x plus etc. plus an phi of x to the n equals 0. The reason why I didn't apply phi to the coefficients, because by the definition, we consider phi, which takes the coefficients to themselves. And as you can see, phi of x, which is r, is actually the root. So what is written here is phi of r, and it's equal to 0. So r must be the root. And now if you compare these two homomorphisms, you will see that they are exactly the same. But let's skip the second part, why every homomorphism of this form. What is more important is to understand how to produce homomorphisms of this specific form. So you just find a root here for this polynomial, and then you take the element x to this root. So you just substitute this root instead of x, and this gives you a well-defined homomorphism from the left-hand side to the right-hand side. So let's explain how to use these in order to compute an isomorphism between these two implementations of F8. So what we need to do, so let me show you. So we have these z2 of x over x cubed plus x plus 1, and we have z2 of x over x cubed plus x squared plus 1. And we want to produce a homomorphism from the left-hand side to the right-hand side. What does it mean? We need to find an element r here, which is a root of this polynomial. So this must be a root of x cubed plus x plus 1, which means that r cubed must be, r cubed plus r plus 1 must be 0 in the right field. So if we can find such an element, then our homomorphism, so we can find a homomorphism which takes a polynomial g of x to g of r. But then you see this is a homomorphism of finite fields. Since it's a homomorphism, it must be injective. So since this is homomorphism, it's injective. So I have shown you that a homomorphism of fields must be injective. Well, because we have two options for the kernel, and the kernel cannot be the whole thing because one must go to 1. But then, since this field contains 8 elements and this one contains 8 elements, it's automatically surjective because we have 8 elements here and 8 elements here, and we are injective, we're actually bijective. So this simply means that every homomorphism from the left-hand side to the right-hand side is automatically an isomorphism. So in order to produce an isomorphism, we need to produce at least, well, a homomorphism. And in order to produce a homomorphism, we need to find a root of the left polynomial in the right ring. So what remains here is to find the corresponding root. So this is the plan. So, but just in case, is it clear what we are, who thinks that it's clear how to produce the isomorphism here? Okay, the Kirill is with me, but is there anyone who more or less is on the track? Yes.
I just didn't get the idea. Why do we need to find the root for left polynomial for the left polynomial?
Because this is your r.
Yeah. But you said we need to find a root for the left polynomial from the
in the right ring.
Yeah. Could you show the definition of the set S, because I didn't get it?
Yeah, the definition of the set S is the set of all roots on the right hand side. So R
okay.
this is
So
the
R from the
okay.
right, and
Yeah, because
for
you
the
want
left.
to move element X to somewhere. So
Okay.
R is the image of X.
Okay.
And since X is, so this is how you should think of it. X was a root of F here. So if you want this to be a homomorphism, you must take X to a root of F here. And it actually works.
Okay.
So yeah, now this is so now we need to find a solution for this polynomial here. Well, how to do this? Well, in what should you do in general? So now the subtask is this. We have this representation for our field, and we want to find an element R such that R cubed plus R plus 1 equals 0. So this is what we want to do. Okay. So what is a naive way of doing that? Well, we know that every element is of this form. So we may substitute it here and solve for the coefficients A, B, and C. Well, we use the reduction, we will get some system of equations, and we want to solve it. That's not a very brilliant idea, because it's very, well, it's not that easy. Okay, so how could we do this? Well, actually, we may try to find a root as a power of X. Well, you see, so let me show you. So let me show you the idea how. Well, I will find the required R in this form. Why? Well, so first of all, well, let's try this. So we want to find an appropriate D such that X to the power of D is a solution of this equation in this field. So why we can find our solution in this form? Well, here is the reason why we can find the solution in this form. Our field F8 has 8 elements. Well, a solution of this equation must be a non-zero element of F8, because if you take R to be 0, well, you will never get 0. So it must be inside this guy, F8 star. But F8 star is a cyclic group of 7 elements. So here you have 7 elements. But since 7 is prime, every element of F8 star is a generator. So it means that this guy is generated by X. So it's generated by any non-zero element. In particular, it's generated by X. So every non-zero element of this field must be presented in the form X to the power of D. And D actually goes from 0 to 6, because we have seven different options. And when D is equal to 0, it's 1, the neutral element, and all other powers go, all other non-zero elements go through, they're just all other non-zero powers. So it's enough to find our element in such a form. So now, if you want to find it, well, so this is one option, just in case. This is the first option, how to find a solution. So now what we need to do, just go use the brute force. Well, D equals 1 doesn't work here, so you just start with d equals 2, and you just go through all the powers and substitute them here and until you find the solution. I'll do this, but before doing that, there is another option. Well, actually, it may happen that you may find a required solution as a linear polynomial. So you may try to go through linear polynomials first. Well, the linear polynomials, they do not cover all the possible polynomials, so it may not work. But if you don't want to go through all the powers, first you may check just linear polynomials. So R and R plus no, not R. You may try linear polynomials first. Well, this need not give you the result because, well, why the heck the root must be linear? But who knows? It may happen that in some cases you can find a linear root. So let's go. So this is like it's not the second option. It's actually let's say 1, 2 primes. Like it's an additional remark where you may find a required polynomial. Okay, so let's do this. So in our case, since we compute in this field of x cubed x squared plus 1, it means that x cubed equals 1 plus x squared. And now we want to solve for r in this equation. And we take r to be x to the d. So what are the options? Well, x is not a valid option because x is the root of the other polynomial. So we start with x squared, then x cubed, x fourth, x fifth, and x sixth. So let's go through all of them. And one of them will give us the required root. So let's start with x squared. Then we need to compute the expression. Oh, I'm sorry for this. We need to compute x squared cubed plus x squared plus 1. Okay, what is this? This is x cubed squared. And what is x cubed? X cubed is 1 plus x squared. So it's 1 plus x squared squared. But now, since the characteristic is 2, raising to the second power is a homomorphism. So this is 1 plus x to the fourth plus x squared plus 1. And now 1 plus 1 is 0, so we can cancel this. And x to the fourth, what is this? Well, x to the fourth is x cubed times x, and x cubed is x plus x cubed. X cubed is 1 plus x squared, so here it's 1 plus x squared times x. So the result will be x cubed plus x squared. And now we can again reduce x cubed to 1 plus x squared. And we can see that the result is 1 plus x. Well, this is not 0. So x squared is not a root. Let's check x cubed. So, but this is the way how you do this. So you just substitute all these expressions here, and you compute until you get the 0. But is it clear how I did the computation here for the second? Who understands the computation here for the second power? Kirill, are you with me?
Yeah,
Okay.
sure.
So is it clear what is going on here?
Yeah.
Oh, okay, because yeah, so I need some feedback, and without your voices, I'm somehow lost. So now you can check x cubed. So what's going on here? So you take x cubed to the power 3 plus x cubed plus 1. Yeah, actually, I don't know which one is the root here, so I have to compute it with you. So here, what you can do, again, you know that x cubed is actually 1 plus x squared. So you do something like this, 1 plus x squared cube plus 1 plus x squared plus 1. Okay, and you may cancel this. So now we want to compute this expression. So this will be something like 1 plus x squared, 1 plus x fourth. Again, using the Frobenius automorphism. And when I expand the expression, oh yeah, and before expanding the expression, I can reduce x to the fourth. I already know that I have computed this expression. You see, well, x to the fourth was x plus x cubed, and x cubed is 1 plus x squared, so this is 1 plus x squared. So here I have 1 plus x squared times x plus x squared. Oof. And now if you expand the expression, you will get x plus x squared plus x cubed plus x to the fourth. And we know that x to the fourth, and again, we can reduce this expression. So x plus x squared, x cubed is actually 1 plus x squared, and x to the fourth is 1 plus x squared. What can we cancel here? So we can cancel these two, we can cancel these two, we can cancel these two, and the result is x squared. So we have computed that this part is x squared, but we also have x squared here. So at the end, we will get 0. Hooray! X cubed is actually the root. And since x cubed is equal to 1 plus x squared, so one of the required roots is 1 plus x squared. So now we see that the required homomorphism from here to here is given by the formula. So let me show you. So a plus bx plus cx squared goes to where? A plus b, here 1 plus x squared, plus c 1 plus x squared squared. And now you can compute the result, well, the result as follows: a plus bx squared, and here plus c cx fourth, and the fourth power, as we remember, is just this expression. So so the fourth power is just 1 plus x squared, and we will get a plus b plus c. So these are let's write everything, and then I will collect the summands: a plus b plus c, this and this, plus bx squared plus this, plus c plus cx squared. Now c and c are cancelled, and the result is this: a plus b is the free term, plus cx is the linear term, plus b plus c x squared is the square term. So the map is given by this rule. The element of this field, which is this one, goes to the element on the right-hand side given by this formula. So this is the final formula for an isomorphism from the left-hand side to the right-hand side. So yeah, so this is how it works. And yeah, whew. Yeah. By the way, just in case, for each, well, in this case, you may find three. Well, you see here, you have a polynomial of degree 3, and you find all roots of this polynomial here. Well, you actually can find all three roots here. You will always find three roots. So there are always as many isomorphisms as the degree of the polynomial. So you can find three different roots on the right-hand side, and you can find three different isomorphisms here. So here, since we have found only one root, we have found only one isomorphism, but there are actually three of them. And this is the general thing. In general, there are as many isomorphisms as the degree of this polynomial. Okay, is it clear what happens here?
Yes.
Okay, so yeah, and so let me see if I want to. Yeah, I didn't discuss the Glow random generator, but it's not that important, I believe. Yep. Probably I just want to make one final remark. So as you can see, when we dealt with finite fields like F8, F4, the cyclic group was of prime order. The multiplicative group was of prime order, but things change when you deal with F16. So when we deal with F16, so it's given by a construction like this. So you need to use an irreducible polynomial of degree 4. But now when we deal with F16 star, its order is 15, which is 3 times 5. Well, in this case, F16 star, well, how many finite abelian groups of this form do we have? Well, we actually have only one finite abelian group, which is Z15. If you remember how to classify all possible finite abelian groups, but it's isomorphic to Z3 times Z5. And what's interesting about this group is that not every element, not every non-neutral element is a generator. So it's more complicated to find a generator here. So if you remember, several seminars ago, we discussed how to find a generator in a finite abelian group if you know its order. So in this case, we need to. So if you want to find a generator for F16 star here, you need to find a polynomial such that it's when you raise it to a cube and to the 5th power, the result will not be 1. And usually the generator of such a group is just X. So usually you may check X and X will be a generator. But sometimes X is not a generator. So usually you should check. So let me go here. So usually you should check G to be X as a generator. Well, if it's a generator or not. And you use the method we discussed earlier. But if it happens that X is not a generator, then in this case, check a linear polynomial. So this is the first attempt. The second attempt, check any linear polynomial where alpha from your base field, which is in our case Z2. So in this case, it will be X plus 1. So there are only one option. So in many cases, the linear polynomials will give you the generator of the corresponding field. And yeah, and the fact if X is a generator or not depends on the choice of this polynomial. For some polynomials, X is a generator of the multiplicative group. For other polynomials, X is not a generator for the multiplicative group. And in any case, if you don't know what to do, all these structures are finite, so the brute force should work. Well, it's long, it's complicated, it's painful, but the brute force method, just go through all the elements and check if it's a generator or not, is a working method. But it takes a lot of time. Okay, and let me just recall how do you check if something is a generator. So if you have a group G of order n, and you can represent the order as the product of primes, then you can, and you are given an element G, how to test if this element is a generator. You just raise it to these powers. So you divide the order, let's say it's M. You divide the order by all prime factors of the order, and you want the results to be not equal to 1. So if all of these inequalities hold, then G is a generator. So this is a generator if and only if all these inequalities hold. But if at least one equality holds, so I mean, then the order of G is smaller than the order of G, and G small is not a generator. So in this particular case, n is 15, 3 and 5 are its prime divisors, so you need to take an element G, and you need to check that G to the 3 is not equal to 1, and G to the 5 is not equal to 1. And so if both inequalities hold, then G is a generator. If at least one of them doesn't hold, then G is not a generator. So this is how you check for this specific field if an element is a generator. And you should start from something really simple like a linear polynomial, and should start from X. For many polynomials, reducible polynomials, here X is actually a generator. Okay, and this is actually everything that I wanted to discuss with you. I know that it took like extra 20 minutes, but I hope it was worth it. At least if you're here, I believe it's at least interesting.
Yeah, I have question.
Yeah, okay. So now it's the time for questions.
I missed it, probably, but yeah, I forgot the question. There was a claim somewhere that all elements of the set are generators.
Oh, yeah.
Somewhere in the end.
Yeah. So let's go here. So where was that?
Yeah, we want to find a solution, a root as x to the power d. Yeah, and we needed this claim.
Oh, where is it? Where is that?
Yeah, here. First point. At the first point.
Oh, yeah. So here, yeah. So yeah. So we know that the multiplicative group has order 7. So it's prime number.
Okay.
So by the Lagrange theorem, every non-identity element of this group is a generator.
Could you repeat the theorem?
Oh, okay. So
probably the lecture, number of lecture with this theorem.
It's I don't remember the number of the lecture. It's somewhere at the beginning, probably the second lecture or the first lecture. I don't remember. So let me. So let me recall. So you just take an arbitrary element here, which is not the identity element, and consider its cyclic subgroup. Its cyclic subgroup must be consider its cyclic subgroup. If you take a non-identity element, the cyclic subgroup contains more than one element, but the order of the subgroup must divide the order of the group. Since it's prime, each subgroup contains either 1 or 7 elements. So if your subgroup contains more than one element, it must be equal to the whole group.
Could you repeat?
Okay, so let me write this down.
Divide something.
So let me write this down. Okay, but what I would suggest is just to read all the lectures again, just glance through all of them, just to refresh what you have read or learned while the previous readings. It's very good idea because, you know, when you learn a lot of new stuff, you just forget all of them. You may understand them and just simply forget. And it's very important to repeat everything. So what happens here is actually you just forget all the minor details that we discussed. it's okay. This is how the brain works. But in order to find with this problem, you need to repeat everything. Yeah, it's unpleasant, but this is the thing that you have to do. So now we have this group. This is our group G, and our group G has 7 elements. So now take any element from F star, F8 star, which is not 1, and consider its multiplicative. Well, it's a cyclic subgroup.
Yeah, should
So
be subgroup of F8.
Yeah. So the order of the subgroup must divide the order of the group.
Yeah, there was something like that.
Yeah. So there are 2 options.
Yeah, whether it's 1
Or 7.
but it can't be 1.
Yeah, since it contains 1 and G, its order strictly larger than 1 because of this. It contains at least 2 elements, so it's greater than 1. So this option is impossible.
Okay, but how do we know that G by G is not 1?
What again?
How do we know that G squared is not 1?
Why G is not 1?
Yeah.
But take any non-identity element.
Yeah, I mean G squared.
Where do you have G squared?
Okay, why the order of this group generated by G is greater than 1?
I don't get it. Could you repeat? What was the question?
Why does the order of this group generated by G greater than 1?
Oh, why it's greater than 1? But what is the order? Okay, so what is the group generated by G? By definition, you consider all possible powers, positive and negative. And the order is the amount of distinct elements here. Okay. Because here you must have the neutral element. It must be here.
Okay, sure.
But also you have G here. It must be here.
Okay.
And they're distinct by the choice. So at least 2 elements are there.
Okay, gotcha. Thank you. And I have another question about bijection. We proved that every homomorphism is an injection, or they're injective. And how did we prove that it's actually surjection?
Oh, okay. For this subjectivity, we use the fact that F is finite.
Okay.
So if we have a if we have an injective homomorphism, suppose that F is a field. So these are fields.
Okay.
And F is phi is a homomorphism. And suppose it's injective.
Okay.
Well, in this case, this need not be surjective. Well, there are counterexamples. But if additionally F is finite, then it's bijective. Because it's injective map between finite sets of the same order.
Yeah. Okay.
So it's a stupid argument.
Okay. Okay, but probably I missed it. Like, why do we have so many nodes there in order to prove that this is we've proved that this is an injection, and after that we spend a lot of time in order to get the result about bijection.
Why did we spend a lot of time about the result on bijection?
Yeah.
Oh, well, we actually spend a lot of time about other stuff, not this one. The part that this is a bijection was actually clear. So we spend a lot of time proving other stuff. So I have to move to the corresponding section of this whiteboard, but blackboard, whiteboard. Yeah, it's not a board with a piece of chalk. You cannot write here with a piece of chalk. You won't see anything if I use my monitor for doing that. Yeah, it's really hard to remember which one is the blackboard and which one is the whiteboard. But okay, are there any other questions, Kirill? Should I?
No, I think, could you just show this piece of blackboard?
Okay. Yeah, it's whiteboard, but it's not blackboard.
Okay.
Yeah, the color is black, but it's not blackboard, it's whiteboard. That's the funny part.
Yeah, the first one column is totally clear.
So here it is. So first of all, we discussed that, yeah, so when we discussed raising to a power of x, we show that this map is a homomorphism. And then this is the place about the bijection. This is exactly literally what I told you. When it's finite, then it's bijection because it was injective and f is finite. So it was short. We spent a lot of time for other stuff, for some remarks and so on.
Okay, got it.
Any other questions?
And in the very top of this column,
Okay.
We have like I forgot, p is equal to 0 or 1 to the power p. We use the fact that x p times is 0. Why is it so?
Here is the proof of this fact.
Yeah, what the data that we have?
Okay, so we have
we have order of 1 equals.
Yeah.
Okay, yeah, it's clear.
Yeah, so everything is written here. So let me do it like this. So you will not skip it. So this is some auxiliary task here.
Okay, and the last question.
Okay.
The very last question about the very
last question.
Yeah, about the very last part of the lesson.
Okay.
What we were doing here.
Oh, what are we doing here? Okay, so
I mean, not this one, but I know probably this one. Yeah, this one. Okay,
so when we discussed F4 and F8, the multiplicative group was of prime order. For F4, it was of order 3. For F8, it was of order 7. So if you want to find a generator for the multiplicative group for F4 and F8, you just take any non-identity element, okay?
Okay.
But now, when it comes to F16, then the order of F16 star is 15. It's not prime. So it's not true that every non-identity element is a generator. So now we come to a question is how to find a generator here. So it's not enough to take an arbitrary non-identity element. So how would you find a generator in this particular case? So what I'm saying here, you just use a general machinery to check if an element is a generator. So you just take a random element of this field, random non-zero non-identity element, and check if it's a generator or not. And as your first option, you should check if an element X is a generator or not.
Okay.
So it may happen, it depends on the choice of this polynomial, that for some polynomials, the element X is a generator. For the other polynomials, the element X is not a generator of the multiplicative group. But, well, if the element X doesn't work, just try other nonlinear polynomial, which is in our case is X plus 1, and it may work. And then actually, as I remember correctly, for all polynomials here, either X or X plus 1 is a generator. So I may be wrong here, but if I remember correctly, so for F16, it does, well, whatever polynomial here, irreducible polynomial you take, one of these guys is a generator. So this is how you should try to find a generator.
Okay, got it. And in the previous task, when we were trying to find a homomorphism between two field of remainders, we had two polynomials, x cube plus x squared plus 1, and another one. And my question is, why why it's impossible to find a polynomial x square in the first ring, for example? Like,
Could you repeat the question?
Why there is no x square polynomial in the first ring?
But there is no x square polynomial.
Yeah,
No, there is x square in the left ring.
but
Oh, you mean
yeah,
you mean these? Why
Yeah.
do I have x here and x
no,
square
no,
here?
no. I was confused. Ignore it.
Oh, okay.
Everything's
So
okay.
yeah, the question wasn't clear to me. So if you can clarify the question, I will
Yeah.
ask.
I thought that there is no second power in this ring. Like that there are only x cube, x and 1. Yeah, no x square.
But here, yeah, x cube, x and 1. Here, x cube, x
No,
squared.
I mean as an element of the ring.
What again?
As an element of the ring that
Oh, yeah,
ring
but
itself contains this element.
yeah, this one is not here because only polynomials of slightly smaller degree are here.
Yeah, I got it. Okay, I think that's all.
Okay, no problem.
Yeah, and yeah.
I think you have another question.
Yeah. When are you going to post the homework?
I hope today, because if I don't do it this evening, then it will be on Monday. So I must publish homework today. The previous time, I just couldn't do that. I didn't have enough time. But I hope today I can post the homework.
Okay.
But just in case, yeah, that the deadline for the previous homework is this Sunday evening.
Yeah.
Because I posted the homework very late because of colloquia. I don't know how to say. Because of the not the colloquia in English. It's called oral test on AMI. Yeah, it was eating my time.
What is MI?
Let me explain this in Russian. На ПМ у нас просто был коллоквиум 2 дня подряд, в пятницу и в субботу, и я просто был в состоянии буратино и не способен был вам прислать домашнее задание вовремя.
Понял.
В этот раз, я надеюсь, это так не будет.
Не сейчас в состоянии буратино.
Нет, сейчас нормально. Сейчас, я надеюсь, я все успею сделать. Ну что, тогда все, ребят.
Спасибо большое.
Да,
Да, все понятно.
Удачи тебе тоже. Кирилл, тебе тоже.